Okay, so I think today I'm gonna explain just a little bit of the exact method, continues, uh, continuing the discussion yesterday about the Excel, and after that I'm gonna explain about the next method, which is called the rigorous method. Okay, so here I'm gonna put the, okay, just put it somewhere here, there. Okay, yeah, and this is the report, and this is the, okay, yeah, so this is the, this one is the report, and this one is the uh, yeah, like that, yeah. Okay, so just I'm gonna just put a little bit of explaining again, so hopefully in the next weeks you can get the assignments. Yeah, you can, so you can have a scratch and then have a start calculation, but before that, oops, we need to click one. Okay, okay, so again in the exact method we have the temperature of the distillate, we have the temperature of the bottom, and we have also the number of tray. Yeah, the number of tray. So the number of the stages. Yeah, not the tray, but the stages. And then we assume that the temperature increase from the distillate linearly, yeah, like this, maybe from the distillate minus bottom divided by the uh, the number. Okay, have you been using Excel in your other assignments? Hello.
For some, I guess, both.
Okay, maybe you're also using Excel in the lab, yeah, in the lab tech. Yeah. So yeah, we have to be familiar with Excel. So I think if I click like this in the formula, you should be able to understand the formula, right?
Yes, both.
Okay. Now, okay, maybe I can explain with the procedure with that is written in this report. Okay, so um, first, of course, we know the enriching, yeah, the enriching the operation, the enriching section, and then first we guess the temperature. So the initial temperature is actually this one, yeah. We actually put this one, the number. So let's copy them, yeah. So the initial temperature is about, it should be about this one. So let's put it back like that. Okay, yeah, put it like that. Okay, now, now by putting the temperature, the next step is, um, maybe I'm gonna put it there. So, yeah. Okay. Okay, so this is our tebakan, yeah, the guessing temperature. Okay, and then first we have the x0, which is the distillate, yeah, this the distillate, and the x distillate also similar with the x0, yeah, from the schematic, and then with the formula you can calculate the xid, sorry, the yid there, yeah, for the formula, with this formula. Okay, and with this y, and then you can calculate the k, which is k would be uh, uh, an equation that you made in the previous one, which is linear to temperature. So find the k of component 1 at the guessing temperature. Jadi buat K pada komponen 1 misalnya pada temperatur tebakan. The first initial. Okay, and after that, once you got the K, and then you do it for all of the formula, and then the next step is you calculate alpha I. Yeah, the alpha I here, there, yeah, Ki divided by KHK. So you got K, alpha I, okay, and then find the XIN, yeah, XI in the first stage by calculate the YIN divided by alpha. So what they do is find the the YI divided by alpha I, and then just summation of all of them, and then they put the XI. Okay, like that. Okay, so then with this calculation, you will find your new XI in the X1, yeah, in the stage 1, which is leaving the equilibrium trait. Okay, we don't know if it is right or not, so what we need to do is we need to find the K. We need to find the KHK from the calculated value. Yeah, find the K, which is KHK is actually the Y1 divided by X1, and this is your KHK. Okay, this should be similar with the calculated KHK from the equation. Okay, so then you have to check with this one, with the KHK, this one, which is calculated, this one, yeah, which is calculated from the temperature. Okay, and then you check the delta, the galat, yeah, this one with this one, and then you will find that one there. There is some differences, so it may not be the good temperature. Okay, so yeah, so nilai KHK yang diperoleh harus sama dengan nilai KHK yang diperoleh dari nilai regresi K value. Jika belum sama, lakukan iterasi. So because it's not similar, so what you need to do with the new KHK, because it is a function of temperature, then find the T, yeah, the temperature. Okay, and then you got, for example, the new temperature based on the KHK. Okay, so then you will have a new temperature over here. Yeah, in this case, the temperature is, if I can go back again. Okay, yeah. So and then they will find that the temperature is actually would be about 54. It's not 55, yeah. And then after that, after you got the 54, you got the 54 from the from the KHK, and then you put it back into the equation, and then you will get the temperature. Yeah, the equation for K value, you get the temperature, and then do again the iteration until you find a very small delta or galat, yeah, from that one there. Okay, so once you get this one, if you get the galat here, so then you will have the operating temperature. So this is the right, and then check if this first stage is a feed stage or not. Yeah, by checking the feed stage is lakukan pengecekan apakah hasil XHK divided by HHK trait tidak beda jauh dengan nilai feed. Yeah, so then this is the HLK divided by HAK of the feed. So and then wait, this one, this is in stage 1, and then for the checking is this one. Yeah, this is the feed, because it is still much larger than the feed. Yeah, this is 0.2 for the feed, while in the stage 1 is still 9. So then it's not a feed. So then we have to move on with the next stage. Okay, the next stage again we use tebakan, yeah, the guessing temperature based on temperature operasi, yeah, this one, plus the delta, yeah, plus the delta there. Okay, add with that, and you got, or maybe just initial one is fine, yeah. Just this one is from the initial one. This is the initial temperature. So the initial guessing temperature is just to put the linearly like this, and then they got the real temperature is around 58, and then you do all of them until you get the checking, the checking for the feed temperature is less than the yeah 0.05, yeah, less than 0.5. So then this is the feed. Okay, now because the HLK divided by HAK not in the stage 1 but stage 6, yeah, in the stage 6 is less than the criteria checking at the feed, like 0.5, yeah, it is less than 0.5. So this is the feed. So that means from the enriching from the top, and then you stop at the stage 6. Okay, so that's the idea. And for the stripping, we should start it from the reboiler, yeah, from the bottom stages. Okay, so again we're gonna start it from the bottom. This is the T bottom, which is the reboiler, yeah. And then you guess the temperature, but actually they got the temperature, but it is also still similar. So the checking criteria is also similar. Yeah, so the stripping one. Okay, so again we need to find the stripping operation. Yeah, the stripping operation, this one, phi dash divided by b l dash, and b and phi dash, and then we got the v, l, and also l dash from the mass balance. Yeah, from the mass balance you can also solve the mass balance, and then find the phi dash and also the l dash, and then put it into the equation, and then you have the operating line. Okay, and again you also know the criteria of checking, which is around 0.52. Okay, so we're gonna start from the bottom. So because we assume that this one there, so maybe you can here they write stage 1 but from the bottom. So first is the reboiler first again, because we know the XB, so yeah, to here. So from the bottom, this is the phi, and then so you have XB, okay, and then you also have this one is YIB, okay, and also you have X XI, yeah, X and -1, yeah, that one there. So first we want to know also it's gonna start with the so again we have to know the temperature tebakan, yeah, and after that once we know the temperature then we calculate the K value, okay, and the K value there, and we also know xb, yeah, because in the reboiler, the y and the x is in equilibrium. Okay, so they have a equilibrium correlation between the xb and also the yib, yeah, the yib over here. So to get the yib, then you can calculate equal to the k1 divided by x1, yeah. So this one based on the k value equal to y divided by x. Okay, so once you know this one, then you can also find the x one as well. Then by also find the this one, the alpha, yeah, or the alpha I, this one there, from the ki divided by khk. You got the alpha there, and after that you want to find there one there, yeah, okay, that one, and then this is the tray, for example, yeah, the tray, and you want to get the x1, and then find the kesetimbangan fraksi uap, yeah, by a xi divided by m plus 1 divided by this one, the alpha xi m plus 1. Okay, again like this, and then you also can find the y there. Okay, and this also the same, so we want to find the new calculated value, and then we need to compare it with the k value from the temperature. Okay, so the basic is the same. Nilai KHK diperoleh harus sama dengan nilai KHK yang diperoleh dari regresi k value. Kalau jika belum sama, lakukan iterasi dengan sama. Okay, so again in here, based on here, again there's a stripping equation, and also there is y equal to kixi, and then you can also find the kesetimbangan, ya, y 1 for this case, the next stages, by adding y m plus 1 and then also x plus 1, that one there. Okay, and then here in this case they have the lowest one for the reboiler, and then the first stage from the bottom, and then they checking, and then they have 3 stages there. Okay, so this is the stages. So apparently based on the calculated based on the exact method, while even in the while we predict 15 stages before, for example, here we find the reboiler there is one reboiler, and then 1 stage, 2 stage, 3 stage. Okay, so here we can see that there are the differences between the shortcut method and also the exact method, but that's fine, yeah. So that's fine, because then actually see, so in essence here, okay, so here is actually the then you have one for condenser, the full condenser. You have 1 2 3 4 5 6 for the exact, yeah, on the top stages, and then from the bottom there are 7 8 and then plus 1 for the boiler, so there are 9 equilibrium stages, yeah. Okay, so based on that, in the exact method they get the 9 stages, while in the theoretical stages for the yeah, from the shortcut method they have 15, yeah. that's fine, because the shortcut method is only roughly, yeah, only roughly, and then it's just a prediction, ya. Jadi hanya untuk menebak saja. So the real fit is actually there are nine stages. Okay, and then here you will in the report, if they didn't do that, but in the report here they can have maybe the profile, yeah, temperature profile. So let's have a look, for example, the temperature profile. So nope. So if I want to calculate it here, oops. Okay, let's up here. So let's, for example, if you want to know the temperature, we can try to have a look. Okay, and asking about the how many comma, yeah, is actually you don't need to put all of the numbers here, because tidak signifikan, ya, the number behind the comma. So I think 2 or 3 is fine, yeah. So this one is nice. So this one is stage 0, for example, stage 2, and so on. And you want to find the graph, for example, there. And then let's make let's make a temperature profile. So see, if you look at the temperature profile, it's not really linear, yeah, it's not really linear, but a little bit drop like that, and then it will increase just a little bit. It's quite linear around here, but it's not much linear. Okay, and then if we check here, the feed tray is in a 6, yeah. So then yeah, so this is the feed tray, and this is the bottom. Okay, so and then if you want, you can also make the, for example, the component, for example, the this is, for example, the temperature, and then also the component 1, for example, component 2, and then so on, and then component 4, and then you may want to find which one goes to the vapor, and also which one goes to the liquid, and then you can also have the profile, and then you can explain what is the what happened with that one there. Okay, later I'm gonna explain this one, but I think it's better with HYSYS next week. So next week I'm gonna explain with HYSYS, so because we can generate the graph much better. Okay, up to here, is there any questions? All right. If not the question, then I'm gonna move on to the next topics about the rigorous method. Okay, a little bit warning ahead. The rigorous method is what we're gonna explain here is actually based on a paper, not paper, yeah, from the books. And in the past, the chemical engineering students did that, yeah, did the calculation. But once we have HYSYS, we have Yeah, we have Aspen HiSys, we have Aspen Plus, we have software. Then this one all calculated using software. Okay, but as a student, we can't only do, okay, so I'm gonna use HiSys and I'm gonna try it like 100%. Yeah. We can't do that as well because we're academics, we're students, and we're gonna be engineers. Yeah, so in especially for this IT, um, zaman IT, yeah, the IT things that which is the computer is everywhere, the programming is everywhere, the Internet of Things is everywhere, machine learning is everywhere. So um, yeah, we also, as a chemical engineers, we also need to do this. Yeah, we have to know about those programming as well. So, what I'm gonna explain to you here is actually an equilibrium-based method. How to get the idea of multi-component distillation, absorption, stripping, and also extraction. Okay, so what is your comment about multi-component distillation? We have learned multi-component distillation about uh, 3 weeks now. So what is your comments? Dama, what do you think about multi-component distillation?
What do I think about?
Yeah. It's fine. What is your opinion? What do you think? It's too difficult, or I don't want to do this, or
I still have problems with it, but I'll revise it on my own. Well,
oh, okay. So yeah, is it difficult
it's just a bit confusing.
or confusing? Okay. Okay, Kevin, what do you think about the multi-component distillation?
Yeah, it's okay, I guess.
Okay.
I don't know what to think about.
Okay. Who loves programming? Do you like programming, Kevin?
Uh, I'm okay with programming, but
Oh,
the
okay.
person I know who's really good at programming is probably Gamma.
Gamma? Oh, Gamma. Okay. Gamma, you're the you like programming?
Uh, yeah, I mean, I'd say I have some programming skills.
Ooh, okay. So then yeah, I think you need to teach all of us. Yeah. I don't like programming, to be honest. uh yeah, right. I think I'm not I when I was students, I really don't like studying all night. And at that time, the one that makes me studying all night is MATLAB, komputasi proses, yeah, with Pak Makarti. And then at that time, um, I can't make the program works. And actually, like I was okay, okay, but at the time I got B. Yeah, so B at the time is good because in my case at that time there is no A B, so from A you get the B. But anyway, I don't like programming at all. But actually in chemical engineering you will have a lot of programming as well. Yeah, MATLAB. And etc. All right. Okay. Okay. So maybe yeah, but we're not gonna do programming here. We just gonna get the definition or the basics algorithm for what happened in the computers. Okay. How about you, Helena? What do you think about the multi-component distillation?
The calculation is time consuming, ma'am.
Okay, right. Time consuming. Okay. What else? Okay, Fatia.
Yes, Bu.
Yeah. What do you think about the multi-component distillation?
I would agree with Helena. It is
Time
very
consuming.
cool.
Okay. How about you, Dia?
I think it's a little bit complicated.
Complicated. Why it is complicated?
Because there's a lot of calculation
A
and
lot of calculation. And which part do you think the most complicated?
which one? Yeah, almost all of them maybe because because I haven't done it, so I'm not really sure too.
Right. Okay, so let's wait until you experience the tediousness of the assignments, okay? But we have to experience that, yeah, because it's a hand-on experience. So you're right, yeah. So but think about it. Our fathers, mothers, or alumni in the 70s and 80s, at the time they didn't have the computer are still in the campus. It's like a big supercomputer at the time, and they have to write programming, at that time to calculate this non-linear and very tedious works. Okay, so just imagine if you want to for example, you want to do separation of ethylene and ethane, yeah, because they have a really similar, just very little gap in the relative volatility. What I read and I try to do it myself in HISIS, they need 99 stages. So imagine how can we do it with this Excel, right? Just so time consuming, confusing, complicated, and sometimes see from, for example, from the shortcut method tell this, from the exact method tell this different way, and so on. So we would say that, but that must be done, yeah. So it is because of the chemical engineering, because of the chemical engineers, we have a huge glory, at around 50s, 90s, and 70s with the oil and gas industries, and then how the oil and gas industry changed the world at that time, to make it more modern, with all the cars, with all the motors. But some of them partly because of chemical engineers can know how to differentiate, how to separate the crude oil into gasoline, after, or diesel, kerosene, and so on. Okay, so we try to imagine and expand our knowledge about the application of the distillation column. And then so this is said that the final design of multi-stage equipment for conducting multi-component separation will require rigorous determination, and also the temperatures. Yes, see, the temperatures is always changing. We have to do tebakan, iteration, for a few times. And also the pressure also may changing, because we assume that pressure is the same, but sometimes we know from the fluid mechanics that from fluid dynamics that there are pressure drop, so then there should be some pressure drop. And also the stream, what happen if we have multiple stream, we have side streams, and also how to measure the stream composition, and also how to measure the heat transfer rate at each stage. So very difficult, but it has to be done, and all the chemical engineers have done that all over the world. Okay, and we also know that in each stage we can solve it with the material balance and also energy balance. The material balance is for example, with the McCabe-Thiele method, from the equilibrium relationship, and also the operating line relationship, the operating line, we can solve that one there. But then if we have 99 stages, or even 10 stages, it's gonna be very difficult. It's gonna be if we want to simultaneously solve them, it's gonna be very difficult. okay, because it is a non-linear algebraic equation. Okay, so but however, around 1970s, with the development of computers, the programming, then the chemical engineers also learn programming, and also they put the routine, they put the the programming for that one, for to high-speed digital computer at that time. Then the solution are achieved fairly rapidly, and then we can get the result instantly. So next week we're gonna have an explanation with HiSys, and also maybe you may want to ask, I don't know, Pak Indra, or ask your teman-teman himpunan how to get HiSys installed in your laptop. So if next week some of you can get HiSys in your laptop, that would be very good, because I'm gonna explain it about the HiSys method to do the multi-component distillation easily. But we, as a students, as a chemical engineers later on, we have to know the inside of the software. Don't try to make just to treat the HiSys as the black box. Don't do that, because we're not salesmen, we're not industrial people. We're academics, we're students, and then in students you need to know what's inside in the programming in HiSys. So this what we're gonna do. Okay, so if we have, for example, there's stage 1, stage 2, stage 3, stage 4, and so on. In each stage, of course, we have the feed. We will have the feed with the FJ, and for example, this is the valve, and the FJ they will have properties such as the composition Zij, Z of I component, and then for example there are 5, 6, or 7 components, and we also have the enthalpy in the feed. We also have the temperature, and also have the pressure. So these are the properties that we have with the feed. Okay, and again, and in this stage, from the bottom there we have the Vj+1, which is a vapor stage from below. And this also will bring the properties with this vapor, including the vapor composition Yij+1, the enthalpy of the vapor Hvj+1, the temperature, and also the pressure. Okay, usually we assume that P is similar, right? But if we have a different pressure, then this becomes variables. Okay, and then it from the top we also have liquid from the stage above, and even this one there is a components, liquid components. There's the enthalpy of the liquid, the temperature, and also the pressure, and they're gonna mix them together in this stage, and then they're gonna leave out with a new equilibrium composition between the Vj and also the Lj. Okay, with Vj with the composition of Yj, the Lj with the composition of Xj. Okay, and don't forget, sometimes in some stage, sometimes there are side stream, or sometimes there are multiple feed. Okay, so if there is a side stream, if in the vapor phase, it's gonna be look like this. We can call it Yj, or if there is a liquid stream from the liquid down there, we can write it Uj. So in general equilibrium stage, we can model that in every stage there are so many variables that may be happened. Yeah, of course, not all of them have the value. If they doesn't have side stream that Wj equal to 0. If they doesn't have liquid side stream, it's also Uj equal to 0. And also, for example, a Q, yeah, the heat transfer, for example, if there is no heat transfer outside, it's also maybe equal to 0. Well, for some cases, for example, if this is in the stage of condenser and then there's a heat transfer positive from those stage, yeah, to outside, then we may want to put the Q. Okay, so this is a generally equilibrium stage that maybe appear to even to distillation, even to later to gas absorption, or even to extraction. Yeah, in extraction also there are, but in the gas absorption we're gonna change V with the gas, and while in the extraction we have, yeah, I think it's also we can just change some of the side stream and so on. Okay, so yeah, this is the same. Yeah. Okay, so then yeah, so this is similar with the previous one. So in any stage they will have all those equipment here. Yeah, they will have a lot of all of the properties here. Okay, the representation of equilibrium stage. The thing is, if we have n stages, if we have so many stages, how can we model it? Yeah, how can we calculate it? That's why for the multi-component purposes, or if you want to put into programming to computer, later on we may want to put it into a list of yeah, a list, yeah, daftar, a list of equation. Okay, so then they come up with a mesh equation. Yeah, a mesh equation stands for mass balance, material, equilibrium. This one is summation. And S is for enthalpy for each stage. Okay, so for in each component, they want to make a mass balance equation to find the this one there. Yeah, so for example, the mass balance here, for example, the feed Fj, yeah, with multiply with the components, the component J, for example, plus the one that goes inside, Xij multiply with L, for example, plus Y Yij plus 1 multiply Vj plus 1, like that, and then minus the one that leave out. So it's basically really about mass balance. Yeah, and then if we write the mass balance, it will become like this. So the L from the previous stages multiply with the X, plus V from the bottom stages multiply with the vapor pressure, and then plus F, and then with the feed, and also the one that leaves out, which is the liquid out, and also the side stream, and also yeah, the vapor, and also the side stream in the vapor phase. Okay, so that's basically the mass material balance equation. Okay, so if we have C components, for example, yeah, C components, then we have So then we have C equation for each stage. So if we have, for example, there are 10 components, so imagine that we will have I and J is about 10, so there are 10 equation of this one. Okay, the second one is the mesh, yeah. Again, the E, yeah, the equilibrium correlation. So this is the mass balance, and the second one is the equilibrium relationship, which is, we know that the K equal Kij, yeah, two component, become that equal to Yij divided by Xij. Yeah, so then it come up with Yij equal to Kij multiplied with Xij, and then we come up with an equation that the equation must be 0. This one is also must be 0, so it come up with Yij minus Kij multiplied with Xij equal to 0. So the idea is to make everyone the equation in one side, so the resulting equal to 0. And again, if we have 5 components, if we have 10 components, that should be 10 components for each stage. Okay, so that is E. The next one is the summation. Yeah, the summation of the components in each stages, and if they have those components, yeah, in those components, then the summation of Yij and also the summation of Xij should be equal to 1. Okay, so if we want to make this one equal to 0, so the summation, so yeah, this is based on the sigma Yij equal to 1. This one also from sigma Xij equal to 1. So if we want to have the equation equal to 0, this also minus 1. Okay, yeah. Okay, so next, the last one is the enthalpy. Again, enthalpy is for energy balance. Actually, all of the mass, we multiply it with the enthalpy in the stream. Yeah, for example, L with the enthalpy of the liquid in this stream, V multiply with the enthalpy of those vapors, feed with the enthalpy in the feed, and also this one is the side stream on the liquid out, yeah, in the enthalpy with the liquid, and also Vj and Wj with the with the enthalpy, and also Q if applicable, if for example in the boiler and also in the condenser, there should be the Q that must be supplied or must be drawn, and then we put the Q as well. So in summary, we have mesh equation. Yeah, of course I'm not gonna ask you to do this for 10 components, of course, because it's gonna be very long and very tedious, and then it needs a lot of programming for that one. Okay, and then we want to, as in mass balance, okay, sorry, okay, yeah, so from we have to also to do the degree of freedom analysis. So here in one stage, in one stage we have Z, Xij, and also Yij. So there are 3, and multiply with the component. Yeah, so if we have 5 components, and multiply with 5. If there's 10 components, that would multiply with 10. So there are 3 multiply the number of components. And aside of that, we also have Vj, Lj, Fj, the pressure, yeah, the pressure in the feed, the pressure in the stage J, and so on. And then this, if we add all of them, it become 10. So in total, there are for the number of equation, there are n multiply with the 2c plus 3, and the unknown yang kita tidak tahu, ya, there are n 3c plus 10 plus 1, which is with this n itself. And for the thermodynamic relation, also we have k value is a function of temperature J, pressure in the J, xij, and also yij. And in the thermodynamic relation also we know that the enthalpy is a function of temperature, pressure, and also the xi, and the enthalpy in the vapor phase is also a function of temperature, pressure, and also the vapor of the mole fraction of vapor. Okay, so all this complicated, but we can get them. Once we know the temperature, we also can find pressure and composition of the stream, and we can calculate the thermodynamic properties of the stream using PVT equation of state and also activity coefficient models. Okay, so so the designing specification, now we have this one, and then also the Z, yeah, the number of components multiply with the composition of the Z. We know, yeah, that we know also the Fj, P, the pressure, the temperature of the feed, P, U, W, and also Q. Okay, and then we still have the remaining of unknown. So the goal of this calculation, of course, is to we want to know the how to get the unknown to solve the problem. Okay, so here I cropped this from the article, because it is very difficult and also not everyone's piece of cake. So then they want to make it to solve it. They want to make it into a 3-diagonal matrix algorithm. You have remembered matrix, yeah, matrix calculation. Remember, if there is A, B, C, D equal to E and F, so we can get sorry, for example, x1, x2, yeah. So then you can get xa x1 plus b x2 equal to E, and also c x1 plus d x2 equal to F. So if we have, for example, n component in the matrix, we also can solve, we can also change the equations into a matrix form, yeah. So then they make this is just one of few methods that are available in the books, also in the literature. They use a three-diagonal matrix algorithm where they want to make a set of equations, yeah. So here they make the from the mesh equation M, E, S, and H, from the mesh equation, they arrange them into a 3-diagonal matrix A, B, C, D. Okay, how to get that? So just arrange them so they're gonna be looks like this in a matrix form. Okay, so in the matrix form, they will have, for example, to make in the matrix form, they will have because, for example, if there is 10 components, then of course they will include xi with stage j minus 1, j, and also j plus 1. So it will include the stage before, the stage currently observed, and also the J after it observes. Yeah. And how to get that, I don't know, yeah, ask them, but they try to change, yeah, they try to change those equation here in order to make this form. Yeah, if you're very curious, you can also try it by yourself. I try by myself also, but yeah, it's not for everyone. So basically they change a, B, and C and D. It becomes like this, and it is actually based on here. Yeah, the modified M equation is obtained by substituting 10.2 into 10.1 to eliminate Y, and substituting 10.6 to 10.1 to eliminate L. So basically what they do is they subtract this one to here, and also maybe subtract from this one into there, and they end up with this type of equation. Okay, so in what is A? A is actually this one, very large. What is B? B is actually this one, very large as well. C is also this one, and D is equal that one there. Okay, and if you want to try by yourself to put it into the matrix, then you will end up with, it is the same, yeah, with the previous one. You will end up this matrix three diagonal. Okay, so for example, let me try to do it. Yeah, so this one 0, 1, 2, 3. So this is become for example A4 1, 2. Okay, A4, B4, C4, and so on. Yeah, so if you want to try to multiply it, you can get an equation now. A1 multiply with x1, A1 multiply with xi1 plus 0, yeah, plus 0 would be equal to d1. Okay, the next one, for example, here you don't have, so 0 multiply by x1, and then you have a2 multiply with x2 xi2 plus b2 multiply with sorry, this one is b1 multiply with x2 xi3, for example, plus c2 multiply with xi4 plus 0 equal to d2. So we actually do with the matrix, yeah, with the matrix calculation, you try to change this equation into the form of matrix. Okay, and we also know, in the general strategy, if we have a three diagonal matrix, you will learn in calculus how to solve them simultaneously. Yeah, you can also maybe learn in computasi process. Yeah, if you have a number of models like this, how to solve it simultaneously there. And also here the value of for each stage, we can solve the matrix for each component to obtain the mole fraction of the component I in the liquid phase at each stage or at the xij. Okay, and then also we can get the xij corrected by dividing xij divided by the summation of xij. Yeah, so this actually tell you that even if we have a very large components, if we have 99 components, or if we have 10 components, if we because it is simultaneously nonlinear, in nonlinear equation, and simultaneously we can put it into the form of matrix as a general solution strategy. Okay, that one there. Another one, we also can compose another set of equation by using enthalpy balance. again, they try to find parameters involving the enthalpy in the liquid and vapor, or in the vapor and the liquid there, and also they have some gamma here, and then they get all of those equations there. Okay, so and then that one also we can get the similar way with the enthalpy balance there between the beta, alpha, and equal to gamma and alpha there, yeah, to find the vapor flow, yeah, the vapor flow. Okay, so in the finish line, or in general, this tells you how the computers or the programs in HYSYS works in the rigorous method, how they can solve the multi-component distillation in the distillation process. Okay, so that's why in that one we have to guess, yeah, we have to guess the temperature, tebakan, yeah, and then if we have wrong temperature guessing, sometimes the calculation can go wrong. Okay, and then they will solve the matrix, the Xij matrix, and then the corrected one, and then you can compute the Tj from the bubble point calculation to calculate the Yij, and then solve the second matrix, and then you find the Lj, and then check the convergence. If it is not convergence, and then we repeat the cycle, and then to get the one convergence in one stage. Okay, and then or not in one stage but simultaneously. Okay, and with that, that's how HYSYS works. And then if we have a good guessing temperature or the guessing pressure at that time, then we can solve the problems. And after that, you can maybe want to compare with the calculation from the multi-component one. Okay, so yeah, so this tells you, of course, after this is only an explanation. There is no assignments, there is no, maybe we'll ask you in the oral exam, but the idea is what you're gonna do. This is what the HYSYS done in your laptops, yeah, what HYSYS done inside the program, but because it's this proprietary, you of course you don't know the inside how to get one. If you want to know the details, it is actually a PhD topics. Yeah, I remember Pa Anggit said that what he's doing in the PhD degree, I think he made like some sort of subroutine or software, yeah, like a HYSYS, that to solve a very specific problem about absorption. Or one of my students, angkatan 2011, yeah, he also has a PhD in Aalto University in Finland, and what he's doing also, he made software for mineral characterization. Yeah, so that is a very PhD project. Yeah, so of course, because you're in undergraduate, you're not supposed to do very detail about this, but this is tell you about the programming skills, also the how the computers has makes us easy, and also we can solve the problem. Okay, so then after that, once you get the all the thermodynamics data and the method to predict the equilibrium phase composition, and then we design the equilibrium stage separation, and after that we can apply the stage efficiency analysis by adding, yeah, the actual design there, and then then it's done. Okay, so that's it, the a very brief introduction about the rigorous methods of the multi-component distillation. This really tells you about very tediousness and very complicated works, but we can do that in HYSYS, and then we're gonna learn HYSYS next week. All right. I think that's all from me. And then before I close this one, any comments or any questions about this? No? Okay. All right. That's fine. Of course, most of them still not make sense, yeah, because you haven't got the assignments. You may want to look at the example of assignments, and I will tell yeah, the others, Grace and the team, also to prepare the assignment for the group assignments. Oh, and before that, let's write the group, yeah. Usually in the in the group for the distillation group, it is determined, ditentukan oleh dosen, ya. But for the packing column group, you can choose who is your friends, yeah. So it's really up to you. But we only have 10 people here, so maybe around only three groups. All right. I think that's all for me. Any questions?
Bu, so about the grouping,
Yeah.
will we choose, Bu?
Yeah, you can choose, but for the packing column assignments. So for distillation assignments, I think we will choose it.
Okay, Bu. And also another thing about the recordings of the class, if it's possible, can you please upload it, Bu, if it's not there yet?
Is it for this week? Oh, yeah.
Yes, Bu.
Yeah.
Okay, thank you very much, Bu.
Okay. All right. Okay. Thank you, everyone, and then have a nice day ahead. And then I'll see you again next week. If you can, have you installed HiSys or not yet?
I think some of us did because
Okay.
we used it in a few
Previous
semesters ago.
semester.
In thermodynamics, you have learned HiSys, yeah, a little bit, yeah.
Yes, so most of us have the version 10, ma'am.
Okay, good. So then you should be ready. Okay, thank you very much. I'm not if there's no question, okay, I'm gonna use my half hour to upload the YouTube things, yeah, to the EduNext, and then I'll see you again next week. Okay, thank you. Bye bye.
Thank you very much, Bu.